Good afternoon. Let's see, got about 18 people on. I appreciate y'all joining. We'll get going here shortly. We're just waiting for Anna from Yodavolt. She'll join here. Oh, yeah, you are here. Hi, Anna. How are you? And we'll get kicked off here. Kicked off here shortly. Here, I'll even turn on my camera too.
Hello.
Good afternoon.
Hello, welcome all to our webinar about SDR. Hello, Haydn.
Hello.
How are you today?
I'm doing great. It's morning here in the U.S. I live in Dallas, Texas. So good afternoon, good morning.
Could you please share to everyone a little bit about your background in NI?
Sure. Yeah. So I guess can you I'll stop sharing my screen for now. But yeah, so I appreciate the opportunity to present here to to y'all's customers. So my name's Haydn Nelson. I work for National Instruments, or we changed our name to NI. I work for the Aerospace and Defense business unit within the organization. I specialize in radar and electronic warfare, as well as software-defined radio. So I'm kind of more on the RF deployments of side of things. I was in the U.S. military and worked in kind of RF and wireless radar research for a number of years, and I've been at NI for about 10 years now, and I've got a lot of passion for this technology, and so I appreciate the chance to get to share some of the stuff we've been working on with the audience today. Thank you all for joining.
Okay. Should I start with a small introduction about our company, and then the stage is yours?
Sure. Yeah. You're in charge.
Thank you. Okay. All right. So we at Yodavolt, we provide test and measurement, design, and lab solutions for engineers and scientists. We started in 2005, and right now we are covering 17 countries in Central and Eastern Europe, with local support in 9 countries, including Greece, Bulgaria, Serbia, Croatia, Romania, Hungary, Slovakia, Czech Republic, and Poland. We distribute and support solutions from top test and measurement manufacturers. We facilitate consolidation for public tenders and corporate procurement. We have developers and domain experts to build your apps. We provide reliable on-site and in-lab calibration services for your measuring instruments. We offer instructor-led online or custom training courses, and we have repair services. Now, our portfolio consists of a wide range of solutions for automating measurements and device control, automating design, validation, and production testing sequences, building research, teaching labs, and services that include training, calibration, repairs, and app development in Labview through a network of partners with extended domain expertise. Now, we've carefully selected our partners to offer our customers the best solutions, focusing on innovation and quality. Our main partner, NI, provides modular instrumentation platforms, including Labview and hardware in several form factors. Cadence, the world best in software for electronic design. Quanzer for controls, robotics, and mechatronics lab equipment for teaching and research. Opal RT that specializes in hardware in the loop systems. Kinova ClearPath for robotics platforms. Etus Research and NI brand for software-defined radio. The equipment Emona LD Didactic for lab equipment for teaching engineering and science. Ametec providing electromagnetic compliance testing. Libelium, Sensi, and other suppliers to integrate sensors in your projects. Digilent for FPGA and microcontrollers. And finally, GW Instec for benchtop test and measurement instruments for your simpler needs. And here are some ways to contact us via email, or you can visit our website and submit a form. So, Haydn, it's all yours now.
Oh, well, thank you for that introduction. Y'all, looking at that list of companies, you know, so Edis Research, the software-defined radio company you mentioned, that's actually, we acquired Edis Research in 2010, and I actually manage a lot of the marketing for those open source radios. So we still maintain edis.com, and I'll show y'all some of these some of the resources that are available for y'all if you're developing software-defined radio applications. So let me go ahead and share my screen. I have a lot of content today. Hopefully we'll get through most of it, and we'll try to make this as let me find my there we are, my display, so I can see the chat. So you know, today, my name is Haydn Nelson, and I was just the agenda for today was I just wanted to talk about some of the trends that I'm seeing in RF system, you know, development, and you know, some of it is pretty relevant in recent news, especially out there, and you know, share, you know, some of the ways that people are using software-defined radio to solve some of these engineering challenges, and then kind of, you know, go through a little bit of these different types of radios that are out there. And one of the things that can be challenging is matching the right radio to the application. So going through some of the different tools that are out there, why you may want to use them. Software-defined radio is a really cool piece of technology, but it also you know, it's also can be complicated because there's, you know, a lot of options out there in terms of different types of radio performance and software tools. And it's kind of like this whole saying of oftentimes you need to use the right tool for the job, so to speak, in that, you know, if you have a if you have a you know, a screwdriver does a good task, and a saw and a, you know, does a different task. And so we'll go through some of that, and if we have time, I have a couple demo systems here at my house, and I'll show you just a brief overview of some you know, just a quick demo of just some simple capabilities in both open source. So I actually have a Linux machine over here and using Labview. So let's get started. And again, I encourage you, since this is really just a Teams meeting, if you have questions or a comment, you know, midstream, feel free to type it in the chat, and I'll address it in real time, or we'll take some time at the end to open it up and have a discussion and address your questions then. So I appreciate y'all joining today, and for hosting this, Yodavolt, Anna, appreciate that.
Thank you for coming here.
So one of the things that we, you know, the electromagnetic spectrum is in it. You know, I'm in aerospace and defense, and it's used for many things. You know, my cell phone here is a 5G cell phone, in that I, you know, it's communicating with the towers, and has a lot of technology built into the communication systems, and you know, the electromagnetic, you know, spectrum is really important on the battlefield, and you know, and it's used in it's the early days of like World War II. You know, it was radar was a you know, really important technology, and over the, you know, the past 100 years almost, the electromagnetic spectrum and the way we're using it has just gotten more and more complicated, and it's been a lot more dense. You know, when you're operating in the you know, electromagnetic spectrum operations, you know, in a country that is well regulated and the spectrum's evenly, you know, is nicely divided up, oftentimes on the battlefield, people don't follow the laws, usually, and so it's really important to have systems that can adapt to that ever-changing, contested and congested environment. Because in you know, things like here in my little cartoon diagram, you know, things like radar jamming, communication systems. There's been a lot of demand that I've seen, you know, with my customers, for being able to rapidly adapt these type of systems to, to essentially, you know, counteract some of the, you know, electronic warfare type things like in the news recently. I mean, I know that it's all near and dear to y'all's heart right now. What's happening in Ukraine. The SpaceX has their Starlink capability, and it shows the importance of the electromagnetic spectrum and being resilient to jamming. They tried to jam some of these SATCOM and internet satellites, and according to the news, if you can believe it, we're unsuccessful, and it shows you the importance of resilient communication systems and how that can really be important to saving lives. And so I think those things are really relevant in the news today on why being able to rapidly deploy new technology, test, prototype it, test it, and get it out there can be, make a huge difference in people's lives, not only on the battlefield, but also like in our commercial lives, being able to deploy new wireless technology for the connected world around us in our smart homes and things of this nature. And software-defined radio is a real key enabling technology, and it's super fun for me to watch. Of course, I have this aerospace defense bent, and one of the trends I've seen in this space is that a lot of these systems on here, this picture here is very complicated, that there's lots going on here. This is a simplified view of the different systems that can be used. And a lot of things, one of the major trends is rather than just something being solely a radar, people are taking these things, trying to reuse the digital processing and the antennas to make combined capabilities where they're fusing multiple sensors with communications, EW radar, all to a single antenna. And that makes it really challenging to say, hey, how do I, I've optimized my antenna for a radar operation. I have an electronically steered array, and I've been I've designed it for this specific purpose. Now I want to have that operate as a communication system. Well, that makes the problem a lot harder, in that you have to take that into account in the design, and in not only in like the RF hardware, but in the signal processing, and being able to, how do you timeshare the assets in the system. And oftentimes these modern systems are including multiple modes of operation. They're including things like cognitive adaptive modes, because when you're in that congested and contested battle space, you need to be able to move on. Someone's jamming you, you may need to move off and transmit at a different frequency, or be very agile. And so with edge computing, people are deploying AI and machine learning type algorithms to the battlefield, so they can rapidly identify signals. And I'll show you some examples of this, the way customers are using our radios to prototype this stuff today, where they can rapidly identify, oh, that signal is a threat, or that signal, that's just Haydn Nelson with his ham radio talking to his friends. That's not a threat, And so being able to rapidly identify threats through machine learning and is become a really popular trend I've seen for people using software-defined radios. And so that kind of went by a little too fast. It's one of these auto changing slides. I didn't test it in that. Okay. Well, I apologize. I'm gonna have to go back here. Let me fix that. I'm just gonna go through this section here outside of the presentation mode, because for some reason it's auto advancing. So this picture here was just talking about some of those trends where we're combining capabilities into a into a common platform where it's radar comms, EW, cognitive modes, and doing that all at a lower size, this SWaP-C size, weight, and power. And so the idea is that people are trying to make these systems where they're fitting on small drones that are a lot cheaper, and you can have 20 drones versus one really expensive drone. And software-defined radio has been a key technology to that. And so NI, in partnership with our partners around the world like Yodevolt, we develop a number of technologies that kind of help in this process. And as Anna showed a minute ago, we have a number of technologies, in Pxi, which I won't go into detail today, but there's a lot of commonality in the architecture of these types of systems, and so using, just depends on your requirements. If you need really wide bandwidth and a lot of fast data movement for your system prototype, maybe Pxi is the right solution. If you need to have a lot of channels and in rapid data movements, not necessarily the need of your application, software-defined radio is a great option. And if you need to be able to rapidly take that IP or even that radio and deploy it into your system and just embed a radio, we have customers doing that with our USRPs. And so it's not really just the hardware, it's also the development software. And one of the things that in software-defined radio is there's a lot of different options for software tooling out there. And I'll talk about, of course, Labview. We are National Instruments, so Labview is a tool that we've developed and love. But there's a lot of really powerful tools out there like MathWorks, Vivado. There's some open source tools I'll talk about. So I guess suffice it to say, for you as the engineer, have a lot of options. And so here I'll go back to this. So anyway, software-defined radio. What is software-defined radio? It's a term that is used quite a bit. And back in the old days, we had like radios that would have like a fixed analog circuit or a fixed function built into them. I kind of use my little cartoon FM radio here as my simple, silly example. These type of radios, it had were purpose-built, designed for that type of modulation that it was receiving, and it could never be changed. It did what it did. It did it cheap. It did it, and then there's OFDM receiver. There's lots of different types of radios. I'm just using this as an example. Software-defined radio allows you to, basically digitizes that whole signal chain and allows you to rapidly adapt to different signal types, both in the transmit and the receive. So it's kind of like a digital sampling. Physical layer is processed in software versus being a somewhat of a hardware function. And so oftentimes this is the architecture, and this architecture of an RF system is if you've ever looked at any kind of RF transmitter, this is pretty much identical. All test equipment looks like this. Inside of NI's vector signal transceiver or some of our Pxi modules, this is pretty much the architecture. This is the same architecture that's in this radio right here. And it's like relatively small radio. This is the radio I'll be showing some demos with today. I have some sitting over here that are actually plugged in. Portions of the algorithm that are physical layer, we say it's not done in hardware, but some of that can be done in the Fpga. And so I'll show you some of the tools that you can, for example, if you're building a system that is a real-time communications jammer, per se, like for a drone jammer, using this Fpga to if it detects a signal, quickly classifies that signal, then needs to, in real time, submit a response to say, knock out like a communications block in that communication signal. Using an Fpga is really the only way that you can get that done in a rapid, low latency way. But you receive your signal, process it on the Fpga. Oftentimes you'll transmit it to a general purpose processor for further processing if you don't need that real time aspect of the system. And so when I say it's not program, you're not have any hardware specific pieces to this. You oftentimes software-defined radios today, some of our more advanced radios have the ability to program the Fpga, so you can get that higher performance inline signal processing. And so, but all of our software-defined radios have this basic architecture. Now the difference is hey, okay, they're all the same. Why do I need to choose? Well, there's a lot of differences in the amount of Fpga processing. A lot of times, sometimes people will use like Raspberry Pis as the processor, and that's not a very powerful processor. So if you need something that can deal with 400 megahertz of instantaneous bandwidth, well, then you may need a much more powerful processor. So choosing the right level of processing, the communication bandwidth from the FPGA to the CPU is important, and choosing the right RF performance for your applications. Most of our radios go up to 6 gigahertz of center frequency. And so if you're working with a radio or working with a signal that's up at, Ka band or higher, up in the 18, 20, 30 millimeter wave, 40 gigahertz type of frequency range, you might have to have some external hardware to use some of these radios, and many people do. And so I'll skip through that. So I guess with that picture of the architecture in mind, there's a lot of different options here. I did mention these Pxi modules. So when we get into the higher frequency, higher performance, oftentimes we address those application requirements with Pxi, and these are test and measurement solutions, and people use them for testing 5G cell phones, for example. But they also have that same programmability that you can use them as in kind of a software-defined radio way, because it's has the ability to program the FPGA on some of these instruments, which is kind of a unique aspect of our test and measurement solution. But on our pure software-defined radio space, we kind of have 4 main categories of radios that people will use for different applications. Some are these host-based, low cost, low size, weight, and power. The one I have over here is, if you can see my camera, this is about the size of a credit card, and a lot of times people use these and deploy them, and make sure that stays plugged in. And those are these B200 minis. They tend to be a little bit lower bandwidth. You don't have as much FPGA space. Now, if you need something that you're going to program that large FPGA, one of our most popular radios is these X310s. I think y'all cover the entire Edis Research portfolio. Is that true, Anna?
If I'm not mistaken, yes.
I believe so. These radios, the X310s, are really popular because they have the ability to swap daughter boards, and you can configure the front end on them. We have different front end options. The widest bandwidth one is 160 megahertz, so you can set it up as a 4-channel receive or a 2-transmit, 2-receive. So there's several different ways you can configure this radio. So it's not just a single product; it's a product with a whole bunch of daughter boards that you can configure. And that one has a large FPGA in it, a Kintex FPGA. Our most modern, so these ones don't have any embedded processing in them. So like it's this picture here, but you kind of can think of it as let me get my pointer out here. It's really just the radio includes only this aspect of the signal chain, whereas some of our other radios, it has the entire system in it, where you have the CPU, the FPGA, and the signal processing front end. And so that kind of comes back to my looks like I killed the presentation. That kind of comes down to like, hey, so if I have something that, to my topic of, hey, matching the right requirements to your application, if I have something that I need to embed in a backpack that goes on is going to be hand carried by a soldier onto the battlefield, I don't know, probably some pretty tough soldiers in Greece, but they don't want to carry a 100-pound radio. I don't know what that is in kilograms. Probably, like 45, I guess. In the U.S., we work in pounds. We're very strange, and we haven't figured out the metric system is a better system than the imperial system, but we'll not go into that. and so a lot of these radios here, the ones that I just showed you, that things that look like this. I mean, people will take these, we sell board only versions and they'll embed them, and so they can you can rapidly prototype on one of these and then quickly embed it into a system. That's really popular in people on the battle space nowadays. Like commercial drones are very very popular for because they're a cheap solution that can be expendable. And so there's a lot of people using these radios to do like counter drone type of systems. And so but the problem with that is you need to have a computer because this thing's got a USB port on the back. So you have to have a computer with the system. So this is not the entire system. Software defined radio requires a CPU in order to operate. And so on these bottom row, several of these with these Zinc processors. So Zinc is a type of embedded processor that has a CPU and an FPGA that's from Xilinx. And so you actually have this CPU embedded. Now these are ARM like RISC, reduced instruction set computer processors that live on these. And you can run Linux and natively on these Zinc based radios. And so that they can operate, kind of headless or independently. And so if you have an application where you just need to have everything in one radio, some of these kind of Zinc-based system-on-chip options are pretty popular. And like even down on these, we call these the embedded series. And so these radios here at the bottom left have rugged capabilities to them. So they have some of that. Conduction cooling already built in, so you can rapidly deploy them. We do have a partner that will take these X310s and can put them in conduction cooled rugged form factors to like deploy them. So this thing that looks like a big stereo amplifier, that's just this radio here, put into a box that's conduction cooled and rugged. There's no fans. Oftentimes if you want something to survive in a dusty environment, having a fan on it is probably a bad idea. We have these high performance standalone radios here too that can operate at some of them at higher frequencies. This radio here is our most recent. You'll notice it has the new NI logo on it. We haven't changed the logos on these older radios yet. They're taking new pictures. This radio is pretty cool. I'm really, a fan of this radio just because it has this Xilinx RF SoC chip in it. If you're not familiar with that chip, basically it pretty much has this entire diagram on one chip, which it has the RF subsystems. Well, it has the A to Ds, DACs, the FPGA, and the CPU all on a single chip, which is really nice because it gives you a lot of integration and control right on a single device. And it has 400 megahertz of bandwidth, so a lot of bandwidth with 4 independent channels. So you have 4 transmit, 4 receive. This is kind of like the high-end sports car of software-defined radio, if you will. So that's kind of the hardware and the different options and why you would choose. Some of these, these tend to be somewhere around. I don't know how the currency differences affected. I know US dollars, and so these tend to be around $1,500 US, whereas this radio here is priced at $20,000 US, just to give you some scale of and that may change country to country. I don't know how they, I'm not on the pricing side. Anna can probably help answer those business questions. but just to give you a scale that these are much higher performance radios, and these ones tend to be probably 3,000 to 5,000 ish, just to kind of just to give you the range of prices here. For some of these options. Actually, one I forgot to mention is we do have one that's this larger radio here. It's called the 2974, and it has an X310 built in it with an Intel x86 embedded processor. So this can be operated as its own independent base station. It's a pretty powerful radio. So the software tools, so that's all hardware. Software-defined radio would not be, software-defined without software. It's in the first word in the name. And there's a lot of different tools out there, and so it depends on within that architecture. Are you talking about the CPU programming, the Fpga? And sometimes people use system models, where they're going to model a greater portion of the system and then plug into that simulation. I gave a webinar not long ago where we were showing off how you can take a USRP and use like the MathWorks radar toolboxes and be able to simulate everything. And then some of our engineers used their radar toolboxes where they replaced their simulated transmitters and receivers for a radar environment with actual real hardware. And so they were able to receive signals and then transmit them. But all the radar processing was MATLAB on the back end. And so they did it all in simulation and then just swapped out the receiver transmitters with the USRPs. So you can, you kind of have this notion of like, going from a model to actually testing it with real world signals. And there's some really cool tools in MathWorks to do that. Of course, Labview has options for programming. I'll give you a demo of this here shortly. And then there's a lot of people that are out there that like to use open source. Linux is very popular, and C++, Python, and there's this tool called GNU Radio, gnuradio.org. It's not owned by NI. It's an open source volunteer army community of SDR tools that NI and Edis Research supports pretty heavily. And so I'll show you what that looks like here in a moment, as well as being, if you're not working within Labview, you can program with open source tools like Xilinx Vivado, and we support both of these modes. So you can program open source directly in VHDL and Verilog, or you can use tools like Labview and Labview Fpga. So it's kind of, SDR is one of these areas where we said I'll be honest, probably about probably about 60-40 or a 50-50 split of SDR users out there. It's probably about 60-40 are on this open source tool chain, and 40% are on the Labview tool chain. So there's a lot more users out there in the open source world than there are Labview users in terms of SDR, deployments. I find that people in academia tend to use Labview more than people in like defense, because they like the free nature of GNU Radio. And so just being honest. And so the differences between Labview and GNU Radio is Labview is very mature in Windows. So I mean, the demo I'll show you today is I actually have a Pxi chassis upstairs that I have a USRP connected to, and I'll show you it. But it's very much a Windows. But we are adding support for Linux. But for some of these, it just doesn't. Some of our tool chains don't work in Linux yet, but we're trying our best to make Labview where it's supported in both Windows and Linux. It's just a little more mature in Windows. GNU Radio is very mature in Linux. And there's Labview is nice because it's for someone who doesn't want to have the simplicity of the programming environment is quite nice. It has a much simpler getting started and installation process. So if someone's new to SDR, it's actually quite user-friendly for visualizing data. I'll show you that. So for those people who like VHDL, C++, and the power of those tools, there's a little bit higher ramp up for using some of these tools. But we have some resources I'll share with you if y'all are interested. And so Labview, if you haven't really used Labview before, I'll just skip right to what a block diagram looks like. And so this is a very simple SDR application where all I'm doing is receiving a signal over the air and then just analyzing and presenting the spectral data. And so, I mean, you open sessions, you configure, you initiate, and you pull the data. This gray rectangle is basically a while loop if you're familiar with C and C++. And you can, this is just sitting here just fetching data and just displaying it. And so this is, a very simple shipping example, and you can go from installing it to visualizing data, even building a quick communication system, in a matter of minutes with Labview. And I'll show you. I have my Pxi system upstairs that I have a little 16 QAM communication system going there. That's what I do at my house. My wife thinks I'm nerdy. But yeah, so that's kind of, Labview as a tool is pretty nice. USRP hardware driver is a open source tool. You can actually look at all of our source code on GitHub. If you let me see here. You go here, I'll pull over a thing. You go to GitHub, Edis Research, UHD, all of our source code is here. You can download it, build it. All of our documentation is here. It's all public. And so some people like this. There's a lot of benefits to this because, one, it forces us to produce better code, and two, if you find a bug, you can fix it. And so USRP hardware driver, or UHD, is our open source driver. We have a similar such driver in Labview, and that allows you to natively program in C, C++, Python. And then within GNU Radio, there's a plugin module called GR, or GNU Radio-UHD, and that allows you in GNU Radio to interface with USRP hardware very simply. And so GNU Radio is a software framework. If you want to learn more about GNU Radio, I suggest going to this website here, GNURadio.org. They have really good getting started guides. In terms of installing and tutorials for using GNU Radio. And so GNU Radio kind of like, I show this picture here on the bottom right, and people think, oh, that looks like Labview. And you're like, well, it is a graphical programming thing, but it doesn't have any loops in it. There's none of those programming structures. It's really a signal processing toolbox streaming architecture for being able to program USRPs. And so there's a lot of information here. The other nice thing about GNU Radio is there's this website here, cgran.org. I reference it here. And if anybody wants a copy of these slides, just email Anna afterwards and we'll send it out as a PDF. And so the cool thing about GNU Radio, I think, a lot of these tools, MathWorks, GNU Radio, and Labview, they all have various different levels of IP you can leverage, so you don't have to reinvent the wheel. And so that's one of the really nice things about SDRs. It's a healthy community of users out there, but there's so many different ways to build your system that sometimes it can get a little overwhelming. But there's a lot of IP, and so this website here is really cool because if you look through here, like, somebody has built a key fob demodulator, which is kind of scary. I guess record someone's key fob. Open your car with a radio. A GFDM is a modulation. There's satellite demodulators. There's lots of IP that people have publicly built, and you can just leverage, which is really, really nice if you're a hobbyist or you're trying to rapidly deploy some new capability. There's a lot of IP out there that can be reused, like 802.11 IP transceiver stacks, OFDM modulators, demodulators, are built into this. So GNU Radio is this. It has this graphical front end called GNU Radio Companion, but that's really just kind of a skin. The underlying architecture is each one of these blocks compiles to a Python, function. And then it's all running in either Python or C++. And this is really just a kind of an ease of use tool that kind of code generates the Python on the back end. So that's a so if your application, you need to you don't want to be locked to an NI radio. Say you're going to deploy to something that's like a rugged deployed system and you need to control all your IP. This is a pretty good option to kind of prototype on a USRP and then maybe deploy to like a custom FPGA system. These are really popular in the defense communities here in the in America for sure. And so I already showed you this website. It's called cgran.org. I guess you can I can put some of this in the chat, is a nice resource for pulling IP. And so that, again, this is not NI or Edis Research IP. I just kind of share it as resources that are out there in this community. And there's just a lot of USRP users in the GNU Radio community. And if you go to GNURadio.org, there's mailing lists that, there's just armies of people who love this stuff that will just answer questions. And it's a pretty amazing thing. So again, there, if you want to take a quick screenshot, if you want, of this slide, and there's a number of websites that could be useful to you. There's a lot of interesting topics that are presented. There's this conference called GNU Radio Conference, and I believe there's a variant that's in Europe as well every fall. Maybe actually I think it's in the spring, when there's not a global pandemic. And we have topics where engineers will come present on the projects that they've built. And a lot of that is recorded and put on YouTube. And so you can actually go and watch some of these talks to learn about what other people have done, or if there's a problem you're trying to solve, someone may have solved it, and you can find someone talking about how they did that on the GNU Radio YouTube channel, which is really cool. I find that it's always a fun. And if you're it'll be in September, even though most of y'all are in Europe, it's all broadcast live on YouTube, all these talks every year, so you don't have to fly to Washington DC to see it live. It's quite a nice event. Some other resources for you if you're trying to get started with these radios is if you go to edis.com and you go to support and you go to knowledge base, there's a lot of resources in here about the different radios and how to use them. Particularly this application notes. I think it's this right here, this application notes page. That's actually a link. There's a lot of really good application notes. And there, one of my favorite application notes is this one here. Building and installing UHD. And so this shows you how to build and install, and it walks you through the process step by step so you can get up and going. But like I said, one of the great things about open source GNU Radio is that it's really powerful and gives you all the control, but there's a little bit of a setup time and a learning curve to using it. But anyway, those are some resources for using these radios in both LabVIEW and and open source tools. And it really depends on the application of what you're doing, of which one I'll kind of go quickly through the FPGA side. There's two ways to program the FPGA. There's this using LabVIEW FPGA, and not every radio supports every tool chain. That's one thing that's a little confusing too. But we have a nice article on, if you go to ni.com/SDR, you go to ni.com/SDR, there's a really nice article here that talks about the different options for different radios. So if you forget everything I've said, these are some other resources that talk about these different radios and why you would use them, what tool chains are supported. So a lot of the things I'm talking about here are in this article. And there's a nice little chart here that outlines each radio and which tool chain is supported. So ni.com/SDR is where that article is linked. And so I'm going to kind of move forward here because we're at 45 after, and I want to show some of these, show kind of some of the demos. I'm skipping ahead here. Well, one thing I did want to show is in those applications that you need to deploy to something like VPX. I don't know if VPX has become very popular in Europe yet. Probably has, but it's a rugged card form factor. And this is one of our radios that's the E320. So kind of, let me step back a few here. We have a portfolio of different radios I've already kind of gone over. The embedded series are these radios that are rugged and deployable, little box that's no fans. Well, this is a standalone unit. and it's called the USRP E320. It's an embedded radio, but a lot of times people wanted this in VPX, and so we partnered with a company called Curtiss-Wright to build a VPX version of this. So I just wanted y'all to be aware that that's available out there on the market. It's a relatively new thing, so it's not like widely distributed. But if there is interest, you know, Anna and I can help get you in touch with the right people. But it's the nice thing about this is you can actually buy these E320s and have like one on every engineer's desk, and it's relatively cheap to prototype. And so the whole idea here is that you don't have to buy a very expensive, rugged mission system to prototype. And so you can prototype and develop on a commercial radio, and then there are paths to deploy onto rugged radios. If this is something that would end up in a tank or a fighter jet or something of this nature, whereas this would probably get destroyed if you put it on like a you know, something that, you know, was launched out of a missile or something, you know. But anyway, so some of the ways that people are using these radios are you know, this is an example of a deployed application where a customer of ours named SkySafe took our USRP X310, built machine learning AI-based drone jamming algorithms, prototyped it, you know, everything with just an E310, and then they just built their own enclosure and they baked it into their product. And then now they're deploying these drone jamming systems onto defense platforms today, and they have USRPs inside of them. And they couldn't have done it as quickly as they did if they would have had to build all that hardware themselves. And they just leveraged all those open source tools that are on the market, and were able to rapidly build this this capability and get it to their customer relatively quick. And so there's other examples of using USRPs for building channel emulators for 5G. This is a commercial application where people are evaluating. A company called Spirent uses our hardware, and we have you know, 5G UE emulators and things of this nature. And so, you know, it's not just defense stuff. You actually can, you know, a lot of people are using this for researching 5G, multi-channel MIMO. You know, this is a company called DeepSig that's based here in the US, but they're actually doing those machine learning algorithms for identifying threatening signals in the spectrum. So it's like a spectral, deep learning spectral sensing application where they're using AI and machine learning to just take that raw stream. You can imagine if you looked at a bunch of spectrum and it's all going by so quickly, how do you identify what's in that spectrum as threatening and what's not? And so deep learning is a real popular area of research. This company DeepSig has a tool called OmniSig sensor that you know, you can think of this as like the spectrum here, and it can rapidly identify like, oh, that's a LTE signal, or oh, that's a you know, a combatant transmitter. We're probably about to get, you know, attacked. You know, and so they have this really nice capability of training machine learning models and then identifying what's in the spectrum. And then there's other examples of using the USRPs for like academic research. So it's not just all defense, you know. One of the really good examples here was Bristol University used our USRPs and broke a record of spectral efficiency, meaning they, for a limited set of spectrum, they were able to, you know, break the world record of passing data using not only, you know, frequency and time, but they also used the spatial dimension. So they used something called spatial multiplexing. And you can see this system behind here that has like hundreds of antennas. Well, they used USRPs to prove this concept, you know, pretty rapidly. And so, but let me do a quick, just, you know, show you a demo. I actually have a system upstairs, but I can remote desktop into it. So here I am now on my system upstairs. And so I was just gonna, you know, show you quickly, you know, the you know, I've installed Labview 2020 and the NI USRP Labview driver. I also have something called our Modulation Toolkit, which has all these different modulation schemes in it. And so, you know, and here there's these, you know, very simple examples. If you install those tools, you can go to ni.com/downloads. You know, all those toolkits should be there. I'm not sure how they, you know, that works, Anna, with y'all in terms of licensing and downloads, but you know, you know, once you install these, you get these these are all just shipping examples. And so here sorry, it's a little laggy because I'm over the network. Can y'all still hear me okay, Anna? Now that I'm remote desktop, I want to make sure my network's still working.
I hear you fine. Yeah, you're just fine.
Okay, great. Okay. And so in this right here, I have a B210, or I have a USRP, one of these, USB USRP. You know, I have a basic transmitter here, and I've set it up as a 16 QAM, you know, transmitter, and I'm taking just kind of random data, mapping that to my transmitter, and you know, and transmitting it. I have these with just antennas. I don't have a camera upstairs, but I just have antennas. And then I have a demodulator here that I can, you know, receive that signal, demodulate it. I mean, the code is relatively simple, where I'm just initializing my radio, setting up some parameters, pulling that data, processing the quadrature amplitude modulation, and then just displaying it. And you can see that I'm pulling my 16 QAM signal. I got my little communication. You know, I could go give one of these to my neighbor, and we could have a little digital comm link here in the neighborhood if we really wanted to. But so it's a real basic example, but I just wanted to show you that I could build a quick comm system, you know, almost you know, really quickly. Let me unshare my screen here, and then hop over here onto Linux, and I can share my screen. I'm logged into this meeting on 2 machines. And so you all should see Anna. Hi. Oh, why won't that go away? So I'm over here on a Linux machine, and for some reason that is not behaving. Sorry. Let me do this. And you know, so here, this is actually that GNU Radio tool I was talking about. And so GNU Radio, this is GNU Radio Companion. So I you know, downloaded and installed this right off of you know, GitHub. So GNU Radio is also on GitHub. And so this is a really simple example here where I have a USRP B200 as well, and the nice thing here is there's a lot of IP that's already built in. Like if you need an OFDM transmitter, a lot of that IP is already built in. There's resamplers, so you don't have to write a lot of this stuff yourself. And so here you can see this block here is a UHD USRP source. And so I'm you know, this is a wideband FM receive. So I'm actually, by a source, meaning I'm sourcing the data off of the radio. So like that's a receiver. It's kind of, I don't really like that term, but I'm putting it through a low pass filter. I'm doing a FM demodulation. So my fancy, this is just a expensive FM radio, if you will. You know, and I can run this pretty quickly, and it has built in these graphical user interface blocks. You can see that down here in the debug window, I'm loading the Fpga. I'm configuring the radio, and then it'll start the application once the Fpga loads. I didn't have the Fpga loaded. Should have run this ahead of time. And there we go. And then boom, it you know, opens this application. You can build in these controls to visualize data. I'm not sure if I'm on a frequency on a station here in Dallas, Texas that we can hear. The sound card doesn't work on this laptop, but you know, I'm quickly able to take an example, get an FM you know, get an FM receive or a demodulation receive, and I have a lot of good examples that I can just like quickly start with. So I don't have to start from scratch each time. And like I said, there's a lot of good IP and out there. And like I said, there's this website here, Cbrand, has a good amount of IP you can use. With that, we only have like 5 minutes left. I went a little long. I apologize. Let me unshare my screen here. Sorry. How do I unshare? There it is, that one. We'll pause there and see if, hopefully, you kind of have a good understanding of the different radios, the different tools. That was a lot of information. I apologize. But hopefully it was useful. And I think this is recorded. I'm happy to, stay a little long if people need to. I don't have anything after this. But if you have any questions, I'd love to hear what y'all are doing with them. So there's
I think you can all switch on your cameras, your microphones, whatever you want, if you want to ask, or by chat. I think I see a question here. Is there some sort of an example or reference project for X410 where one can freely modify the FPGA image to fully take advantage of the RF shock, if I see correctly, chip?
Yeah. I'm pretty sure there is. That's a relatively new radio. We have built demo systems that put like a FFT on the FPGA of the X410. I guess, and if you want to, take, I'm gonna totally mispronounce your name, Tomakovsky's contact information. We can put you in contact with some of our apps engineers, and point you to that. Let me look right now on the Edis knowledge base, because there should be, and there might be an example on GitHub, but I'm not sure off the top of my head, but I will find out for you. Edis.com/support knowledge base. Yeah, that's a good question, because the RFSoC is a cool chip. It has a lot of capability in it. And that has to exist because we've programmed it with our apps engineers, so there has to be one out there. I just don't know exactly where to point you to immediately, but we can find out. Any other questions? It's a cool radio. I was heavily involved in the final stages of finalizing that product and launching it. And so if you ever go to ni.com/SDR, there's a demo video there. And that was, me and a company called 3DB Labs who did this signals intelligence demo, which was pretty cool. I actually have a copy of that software on that laptop right over there.
I think there is one more question here.
Is there any possibility to set delays between the channels on the 2954? What do you mean by that? Like on the FPGA, in order to transmit the same signal or a delayed on a set, so like you're transmitting two signals and one of them is delayed to each other, like that? Or are you talking about receiving one and then delaying it and transmit? Oh, so you're kind of controlling the phase of the relative signals. There's something called time commands, but if you really wanted the ultimate control, you can build your own little memory buffer time delay blocks, and use the RF network on chip. So the 2954, it depends, are you using Labview or open source? But it is possible. You may have to build your own FPGA IP to do it. You're using Labview. Okay. Because in open source, there's a thing called time commands that you can use to set the transmit time per channel. And so you may have to use Labview FPGA to build just an IP block, but that's a pretty simple operation.
Actually, I wanted to ask you about Python and if there are any options for Python application development.
Say that again?
I am talking. I'm Anna. I don't know if you see me.
Yeah, you can hear. Sorry, it broke up there for a second, but could you repeat the question?
Okay. I wanted to ask about Python application development.
I'm having a hard. Can you type it in the chat? I'm having a hard time.
Sure.
Actually no, I got you. Sorry, I was having a hard time. Now the Python app development. So yeah, like I said, so Python is actually, let me ask that to the group. Is a lot of people program in Python out there in the engineering world? I use it a lot for if y'all need to drop, we're 1 minute out. I take no offense. Thank y'all for sticking through the whole time. I can stay a little longer if people have questions or are interested. I truly appreciate the time, and hopefully this was a valuable use of your hour and interesting. So Python is really popular because there's a lot of IP out there. GNU Radio is based on Python, so you can program in Python or but also in Labview we have Python plugins in Labview. So the wonderful thing about USRPs is that you can program it in so many different ways, and so it's like it's never an easy answer. But you can actually do Python in Labview, and you can also GNU Radio is based on is built in Python as well. Any other questions or anything else you had on your mind, Anna? I appreciate the coordinating.
Well, if someone has any questions, you can always email us at info@yotovolt, or you can use marketing@yotovolt.com for if you want a copy of the presentation that Haydn just showed. And I think I see one more question here about GNU Radio.
So you mentioned that GNU Radio does not have some Labview programming aspects. Are there any alternatives? Well, like what I meant was, so don't miss. I guess I don't want to I want to be clear in that. So think Labview at the top level has things like for loops and while loops and very these type of programming constructs. But in GNU Radio, you have those same constructs. Just that top level GNU Radio companion tool that I showed. I don't have I'm not logged into my demo system again, but once you code generate Python has all those same programming constructs. So no, don't misinterpret to me to say, hey, you don't have those programming aspects. You do, just you got to do them in Python or C++, and so it's just really at that top level. A lot of times the GNU Radio Companion doesn't have while loops and for loops and shift registers and things like that. Those programming constructs that you have at the top level in Labview, you have the same capabilities. Just GNU Radio, when you hit run, it code generates Python, and then you can go in and edit the Python. And that's a lot of what usually people use GNU Radio Companion to just code gen that first step, and then they go in and modify the Python, or the C++ directly. So you have those abilities. So don't miss. I probably said that too fast. I apologize.
Right. I think we are past our time. I don't want anyone keeping. If there is no other question, I can give you all a second if you want something, but I think we can wrap this up.
Sure. Well, thank you again, and thank you all for your attention. We really.
I think we have time just for one more question. And then
Are there any SDRs that would go under 56 megahertz, like an HF radio? The X410, I actually here let me share my screen real quick for that question. This slide here is kind of, whoops, y'all don't want you to see my teams. This slide here shows you that where you got some of the radios go down to 1 megahertz. This X410 is our lowest frequency radio. We do have the ability on these X310s. Like I said, there's these different daughter boards that are out there. Let me pull up the web page here. Edis Research, if you go to products, RF daughter boards, there's a lot of different daughter boards that are compatible with the X310s. Some of them, we have one of them that's it's called an TX LFRX. Where is that at? It's this LFRX that goes down to 0 hertz. Basically goes down to DC. And we have so this is low frequency stuff. So yeah, those options absolutely do exist. A lot of times, one of them, a friend of mine who's a professor at University of Massachusetts Boston, he uses this board. And he uses it to modulate LEDs and does light communication with a USRP. So he's using an SDR, but modulating pulses of light to communicate, the light fixture in your house, talking to your cell phone. And he uses the X310 with these low frequency daughter boards. So those options, that's one way you can get down to those really low frequencies. Anyway, hopefully that answers your question. Lot of information. I appreciate. This stuff's super cool, and I'm so thankful to NI to allow me to have these cool little radios and get to share some of this with y'all and help. And I love seeing what people do with these radios, like the real world impact of people using these to help aerospace defense applications, to help save lives, to developing the next generation 5G. I just think it's really cool to see, to kind of be cursorily a part of some of that. So anyway, any other final questions, or do you want to shut it down, Anna? I'll keep going for hours.
Thank you. This is really nice. I don't see anything else, to be honest. So, okay, again, if you have any questions, we are happy to help here at Untitled. And for the slides, you can email us. Thank you so much, Haydn, today for this exciting, interesting webinar. And we hope we can meet again and show some more stuff about SDR.
Actually, one last thing is, go to ni.com/NIConnect. If we're going to be having our big NI event, Yodavolt will be there. I'm going to try to meet y'all's CEO in Austin. We have an event in 3 weeks in Austin, Texas, but we're going to be doing a big event in Munich later in the year. So kind of keep an eye out for that, and that'll be an opportunity to meet some folks in person, see some of this technology live, and collaborate and connect with some of your colleagues in the industry.
Thank you.
Yeah, thank you.
All right. Thank you all. Have a nice day. For you, Haydn, it's a whole day ahead. So thank you all for coming.
Have a good day.
Thank you very much. Bye-bye, everyone.
Bye.